Welcome to Ask and Learn.
We want to use some kind of CAS software to graph the function f of x is equal to x to the 2/3 over x to the 4th plus x plus 1. And then we also want to use this to find the first and second derivatives, as well as to graph them. And once we graph the derivatives, we want to find intervals of where the function is increasing, decreasing, concavity, as well as any extreme points we may have, as well as any inflection points. So I went ahead and graphed f of x already. So now I just went ahead and zoomed kind of far out and looked to see if there was any behavior towards the ends I might care about. And in this case, I think the best window for us to view would just be from -3 to 3. And we get this nice looking curve here. So just kind of looking at this, when we take the first derivative, we know we should have some kind of maximum, maybe around like -0.8. We should have a minimum at x is equal to 0, or it may be undefined at that point because it kind of looks like it's really pointed at that point right there. And then we're going to have a maximum around 0.5, it looks like. So now that we kind of have an idea of where we might have some of our maxes and mins, let's go ahead and see what we get for the first derivative. So I went ahead and plugged that equation into a derivative calculator, and it gave us this for our derivative. Now, one of the things we're going to have to remember is, so normally for critical values, we just look for where the function is set equal to 0. But we also have to remember that if it's undefined, we need to check those points as well. And in this case, we have a vertical asymptote at x is equal to 0. And so we know that x is equal to 0 could be a possible critical point for us. So let's just kind of look through this. Because if we go back to our original one, we see that this is going to be defined for all real numbers. All right, so let's go ahead and find where the function is increasing and decreasing. Now, to the left of -0.722, the function should be increasing because remember, if f prime of x is greater than 0, that tells us we are on an interval where it is increasing. So to the left, it will be increasing, and to the right of that point, it will be decreasing, which tells us we should have a local max at x is equal to -0.722 about. Now, for our other point over here, well, it's increasing into the point and then decreasing after. So again, we're going to have a max here. And now about 0, so I'm just going to go ahead and write this over here. So about x is equal to 0. So to the left of our horizontal asymptote, or vertical asymptote, the function is negative, so it's decreasing into x is equal to 0. And after it is positive. So here that we get at x is equal to 0, we have a local minimum. All right. Now that we know what values for x are maxes and mins, let's go ahead and write down these intervals. So f of x is greater than 0, so it looks like starting from -infinity all the way up to our first x-intercept, so -0.722. And then it becomes positive again after 0, and then it'll stay positive until about 0.611. So that's our interval where the function is increasing. Define decreasing. Remember that is when f prime of x is strictly less than 0. And that's just going to be the rest of our interval here. So from -0.722 up to 0, and then union 0.6112 to infinity. All right, now let's go ahead and check out our second derivative and try to find some concavity. So just like our first derivative, we're going to have this vertical asymptote at x is equal to 0 now. So we may need to check to see if this is an inflection point as well. But let's first check these 4 x-intercepts that we have. So to the left of negative 0.966, it looks like our second derivative is positive. So remember, f double prime of x strictly greater than 0 means we're going to be concave up. So we're up, and then after that point it's down. So that means here we will have a point of inflection because concavity changes. Our next point, well, it's concave down to the left and concave up to the right, so point of inflection. Our next 0, which is right here, let me go ahead and do this one up here. So it's concave up to the left and concave down to the right, so that's also a point of inflection. And then over here at 1.115, it is concave, not concave up, but concave down, because it's negative to the left of it, and then concave up to the right. So that would also be a point of inflection. Now, just like before, let's go ahead and check out 0. So x is equal to 0. So to the left of x is equal to 0, the function is negative. And also to the right of x is equal to 0, the function is also negative. So that means it's concave down on either side. So that means this here is not a point of inflection. All right, so now let's go ahead and actually write out our intervals. So this is going to be negative infinity to our first x-intercept, 0.966. And then we'll union that with negative 0.456 to negative 0.123. And then our last interval of where it is positive will be 1.115 to infinity. Then when f double prime is strictly less than 0, we know the function will be concave down. And this will occur on negative 0.966 to negative 0.456 union with negative 0.123, and let me zoom out a little bit, to 0, and then 0 to 1.115. So we have our intervals where the function is concave up, concave down, and all of our points of inflection. So we're done with the problem now.